Hello and welcome. The transformation of materials into different phases are critical in controlling their properties and performance. How long do they take? How do they take place? How can we control the transformation to produce a desired microstructure? How do we map and quantify the transformation as a function of time and temperature? These videos introduce the mechanisms and time dependence of phase transformations and show how to generate and read a so-called TTT diagram, where the path of the transformation can be quantified as a function of temperature and time. I hope you will find them useful and informative. In this video, we'll describe what a phase transformation is. We'll talk about why they take place and the undercooling and supercooling of liquids. We'll get into how phase transformations take place, and we'll talk about nucleation and growth, their rates, their mechanisms, and their temperature dependence. We'll then move on to the overall transformation rates, and also discuss how the transformation rates affect the final microstructure of the material. Phase transformations are ubiquitous in material science and in life. They take place when a change in the external conditions, for example temperature, cause a material to change its form to a different phase. There are numerous examples. Here we'll focus on condensed matter transformations, namely the solidification of liquids below their freezing point, as well as solid-to-solid transformations in the iron-carbon system. Even when a new phase is stable, the transformation from the parent phase takes time. We refer to that time dependence as the kinetics of the transformation. Because the kinetics can be very slow, it's often possible to preserve the unstable form of the material below its transition temperature, a process known as supercooling or undercooling. A well-known example is the supercooling of water. We can cool water well below its normal freezing point, and if it is pure, it will not immediately transform to ice. This bottle of water is taken from a freezer at -25°C, and it's still a liquid. It would remain so for a considerable time unless we give it some help in removing the barrier to crystallization. In this case, by adding a so-called seed crystal, which immediately causes solidification of all the water. How does a phase transformation take place? What is the mechanism? Well, for most transformations, it occurs via a process called nucleation and growth. For example, here is a beautiful slow-motion video of ice crystallization that shows this two-step process. You can see the crystals start to form or nucleate throughout the liquid, and then they rapidly grow into larger crystals. Let's take a look at a couple of videos that give a very realistic, atomistic view of what's going on and considerable insights into the nucleation and growth process. Again, for the solidification of a liquid. The initial stage of nucleation or incubation can take significant time. Here the atoms are attempting to stick together to form small nuclei. After enough atoms cluster together, they slowly organize into an arrangement that starts to resemble a crystalline structure. The clusters eventually reach a so-called critical size that is large enough for them to grow. Next, we have the process of growth. In this simulation, hopefully you can see the small yellow-colored nuclei trying to form throughout the liquid. They come and go in different parts of the liquid as they try to organize. When they reach the critical size, growth will begin. Here we go. You can see the middle stages of the growth can be very fast. And then, as the conversion is almost complete and the liquid is consumed, almost, the rate slows down as the final amounts of liquid solidify. Let's take a look at some issues we'd like to understand. We'll stay with the example of liquid solidification. First, if the solid is stable, i.e. if it's below its freezing point, why doesn't it just grow immediately when it's cooled below that temperature? Something must be resisting the transformation. And the answer is that the resistance comes from the interface between the solid and liquid phases. This is unstable and high energy as there are strains at that interface. How does the phase transformation take place? We've already seen it occurs via a nucleation and growth process. But we'll need to dig deeper because the rate of the transformation depends on how far below the freezing point we cool the liquid, i.e. the degree of undercooling. Does the rate of transformation have any effect on the final microstructure of the material? Yes, it does. For example, for a small amount of undercooling, fewer solid nuclei are formed. We'll see why later. And therefore, when they grow, there are fewer and fewer larger solid grains after the solidification is complete. In contrast, a larger undercooling results in many more nuclei, and the solidification is completed when these grow and form much smaller grains. Again, we'll explain why later. Let's take a step back and think about what is needed to form a new phase. First, the new phase, here a solid, must be thermodynamically stable, i.e. it must have a lower free energy and there must be a driving force for it to form. Here's a schematic plot of the free energies of a liquid and a solid as a function of T. Above the freezing point, the liquid is stable, and it has a lower, more negative free energy. Below the freezing point, the solid has the lowest free energy, and at the equilibrium freezing point, 0 degrees C for water, their free energies are equal. That is why the freezing point is the only temperature where the two forms could possibly coexist at equilibrium. As we drop further and further below the freezing point, i.e. as the undercooling increases, the driving force for freezing increases. We can quantify the temperature dependence of the free energy of freezing from the enthalpy of freezing using the equation shown. We'll use that later on. What else is needed to form a new phase? Well, we need nucleation of the new phase. There needs to be an incubation period for the atoms to stick and form embryos that gradually organize into solid nuclei. And remember that previous slide, we saw the simulation of that happening. So before growth can begin, they must reach a certain critical size to be able to overcome the unfavorable energy of the interface with the mother liquid before they can grow. This critical size, which we denote by using a radius r star, is temperature dependent. And as we'll show in a second, the critical size required for growth decreases as the degree of undercooling increases. So now let's calculate how large the nuclei must be before they can grow. Well, to figure out the size required for growth, we need to consider the favourable and unfavourable energies that are involved. The favourable energy is the thermodynamic driving force for forming the solid, delta G freeze, which we described previously. If we multiply this by the volume of the nucleus, assuming a sphere, this is 4/3 pi r cubed, then we can calculate the lowering of g that results from the formation of a solid nucleus with radius r, and that's shown. The unfavourable energy is associated with the interface between the solid and the liquid, and that interface has a positive energy called gamma solid liquid, and this is the energy per unit area of the interface. The positive free energy change from the formation of the interface scales with the area of that interface, 4 pi r squared for a sphere, and is given by the equation shown. By adding these two terms, we get the following for the change in the total free energy when a liquid transforms into solid nuclei. We have these two terms, the favourable and the unfavourable. Now we can plot the favourable and unfavourable parts of our equation as a function of radius. We see the favourable term becomes more negative with an r cubed dependence, while the unfavourability of the interface scales with r squared. Therefore, their sum, delta G total, shows a maximum at a certain value of r, which we call that critical radius, r star. R star is the size required for spontaneous growth of the nucleus. Why? If r is less than r star, any growth increases delta G total. However, when r reaches r star, the growth lowers the delta G total, and it will proceed spontaneously. Taking the differential of delta G total with respect to r, we can obtain an equation to calculate the value of r star. We see, for a given system, with a given gamma, T freeze and delta H freeze, the critical size for growth decreases as the degree of undercooling, delta T, increases. In other words, as temperature is lowered further and further below the equilibrium freezing point, the size of the nuclei required for growth becomes smaller and smaller. The dependence of critical size on the undercooling is shown here for a given system. At lower T, which is a higher undercooling delta T, the increased stability of the nucleus allows it to overcome the interfacial energy with a smaller r. So this would be our more undercooled sample. This would be less undercooled that requires the higher critical radius. Now, given the size for growth is reduced, then the nucleation period should be faster. More nuclei will form, and that will in turn result in a smaller final grain size when the transformation is complete. The critical size for the nuclei is typically in the range of a few nanometers, perhaps between 1 to 15 nanometers. We can use the formula for R star, and if we assume spherical nuclei, we can plug in available data for the energy of the ice-water interface and the enthalpy of freezing to calculate R star for the solidification of H2O. When we plug in the numbers shown here in this table, we see there is a rapid decrease in the size of the nucleus required for growth as the temperature decreases. So when we go to 60 degrees undercooling, that R star is around about 1 nanometer, whereas for 5 degrees undercooling, it's 11 nanometers. Knowing the volume of a mole of H2O, we can also translate those radii into how many H2O molecules would be present in the nucleus at that critical size. Not many when we go to larger undercoolings. Just 90 H2O molecules when this R star is 0.9 nanometers. Now we'll look at how the rate of nucleation, which is the number of nucleation events per unit volume per second, changes with temperature. By convention, the nucleation rate is actually given the symbol I for incubation. From before, we know the rate should increase as the undercooling increases, because of the increased driving force that's reducing the critical size and producing more nuclei. So we'd expect our nucleation rate to dramatically increase as we lower the temperature. However, as the temperature becomes very low, the mobility of the atoms is reduced, and this counters the delta T effect, and the rate will be reduced at lower temperatures, back down. Therefore, there is an optimum undercooling, a sweet spot where we can maximize that nucleation rate because of these two competing factors. When the nuclei reach the critical size, growth of the new phase can begin and the old phase will be consumed. The growth rate, G, is the rate of increase in size of the growing particles in meters per second. Growth is diffusion dependent. So how would you expect this to change with temperature? One might think that a higher temperature, i.e. a lower delta T, should result in a higher growth rate because the diffusion coefficient always increases with temperature. However, there's a trade-off, because the rate of diffusion also depends on the driving force for atom movement, i.e. the difference in the stability of the atoms in the two phases. Technically, this is the difference in the chemical potential of the species in the two phases. We know the driving force increases with delta T, so this would favour increased growth rates at lower temperatures. Therefore, with the diffusion coefficient favouring higher growth rates at smaller delta T's, and the driving force favouring higher growth rates at lower T's, when combined, these two opposing trends result in an optimum delta T, an optimum undercooling, where the growth rate is maximised here. Well, we just saw the nucleation and growth rates are maximised at given undercoolings. The maximum for the nucleation rate, as it turns out, always lies at a lower temperature, a higher delta T. Well, we're interested in the overall rate of the transformation, which we'll call dx dt, where x is the fraction of the new phase that's being formed. Dx dt is proportional to the growth and nucleation rates. Combining the two nucleation and growth rates then, to get this overall rate, we see the optimum undercooling to achieve the fastest overall rate lies between the maxima for G and I. If we want the phase transformation to take place in the fastest possible time, this is where we need to be. In the next part of these videos, we'll look at how we can use these rate curves to plot the extent of the transformation as a function of temperature and time, and we'll generate the so-called time-temperature transformation, or TTT diagrams.